You can create an infinitely large sentence that is made up of many smaller sentences. Now that may seem simple enough, but what if I asked you to make a sentence of chess moves that summarizes the possible ways in which this chess game could go on? You probably won't feel like trying. However, what if I said, here is a computer that can rate a chess position based on how well you're doing, and you can use it, but for only one position at a time? Could you solve this problem now? Well, you could take one position, ask the computer to rate it, and then move a piece. You could then ask it to rate that position again. You could do this until you've reached every possible position. Of course, in reality, solving chess is a little more complicated than this, but this way of thinking promotes one of the most important ideas in computer science: recursion. The idea of this video is to give you more than just an intuitive understanding of recursion and display the real benefits of it in fields like engineering and optimization, and why it's one of the most important concepts in computer science. Arguably, one of the most famous examples of recursion in mathematics are the Fibonacci numbers. One of the ways to define the Fibonacci numbers is to define each number as the sum of the last two, starting from 0 and 1. This gives us the sequence 0, 1, 1, 2, 3, 5, 8. If we start from 8, we can build a tree of Fibonacci numbers. This means that to find, for example, the fourth Fibonacci number, we would have to find the third, and then to find the third, we would have to find the first and the second. Now you might have noticed that the first and the second Fibonacci numbers are already known. This is to make sure that we don't go back infinitely. This is where a high school mathematics concept that you might have heard of called induction comes into play. Now let's imagine that a friend tells you that they found the largest number, and let's say they say something like 1 Googleplex, which has 10 to the 100 zeros in it. Well, you, my intelligent viewer, will say, hold on, let's think this through. The smallest natural numbers I know of are 1 and 2. I know I can add 1 and 2 and that makes 3. Now, nothing stops me from doing the same thing with the number you said. So there must be a number bigger than yours. In this scenario, 1 and 2 are your base cases. And you made a leap from 2 to a bigger number and then made the same argument. Believe it or not, after this you already have the necessary tools required to understand recursion. Donald Knuth, a famous computer scientist, talks about how a post office sorts its mail so that it reaches its correct destination. One way they might do this is by first sorting the mail by a large geographical area, like country, then by state, and then by city, and so on until it reaches the correct destination. Recursion allows us to think in a similar way about huge problems by breaking them down into smaller pieces. This is also known as divide and conquer. Let's talk about one of the most famous problems in computer science: search. Specifically, searching for a magic number in a huge list of sorted numbers. Well, one way you might think of is to start from the first place. See if you found the number. If you have, then you're done. Otherwise, you go to the second place and so on until you either find the number or you reach the end of this list. If we want to measure the amount of work we have to do to find our magic number, we can count the number of comparisons we have to do to reach this number. If we have a list of n numbers using the method we just saw, it would take us, in the worst case, n comparisons. This is if the number is not in our list, or at the end. Let's call this method obvious search. The question I have for you is if we can come up with something quicker. Pause the video if you want to come up with your own way of solving this problem. I'll wait. A better way to solve this problem is to see if our number is in the center of our list. If it isn't, and our magic number is greater than the number at the center, then we can completely discard the first half of our list. Why does this happen? This is because our list is sorted and therefore all the numbers before the center are less than the numbers we want. We can do this again with the second half of our list, and so on until we find our number. Well, you might ask, why is this better than obvious search? Let's count the number of comparisons. For a list of size n, which in the worst case scenario does not have our magic number, we will first divide our list into half after our first comparison, then into 1/4 after our second comparison, and so on until we reach one number and realize that our magic number is not in this list. So we did the same number of comparisons as the number of times we would have to divide our list into two pieces until we reach a list of size 1. In other words, we do the natural logarithm of n comparisons. If we had to write this in pseudocode or in our amazing programming language, it would look something like this. What we have arrived at is not non-trivial. For a second, let's compare the number of comparisons it would take for our obvious search versus our binary search to find a number in a list of these many numbers. For our obvious sort, it would take 2 to the 100 comparisons, which is basically the length of our list. On the other hand, binary search would just take 100 comparisons. All it took to do that was breaking down our problem into a few subproblems. This method of search is used in some satellite systems to narrow down possible frequencies to communicate with satellites. It can be used to guide missiles, find shorter routes, and so much more. An equally important algorithm, merge sort, is also based on a similar idea. Aside from algorithms, recursion can also be used to think of ways to represent things in our world. Let's say you really like gambling. Your friend tells you to pick a card from a deck and let him repeatedly pick cards. Every time he picks a card, he shows it to you. You have the option to leave or keep playing. Every time you stay, the money you lose or win doubles. You win if the last card is numerically lower than your own. Such a game can be modeled as a tree of decisions. At each moment in the game, you can evaluate your next decision by thinking about the possible outcomes, and then their possible outcomes, and so on. Although this way of thinking is unlikely to help you make it big in Vegas, it is still helpful because now you can see how things in our world can be modeled as recursive structures like trees. In the next part of this video, we'll discuss a famous example of this. Let's say you're a creative startup founder that wants to make their own music app for people that like songs with guitar solos. You want a way to recommend new music to people. The way you thought about involves the following steps. First, every time the user listens to a song that has a guitar solo of maybe 1 minute, you recommend songs to the user that have guitar solos that are of less than 1 minute. And you want a fast way to do this. Can you think of a good way to solve this problem? One way is to store all the songs on your app in a binary tree. What does this mean? Let's say the first song has a guitar solo of 50 seconds. Then your binary tree would look like this. Nothing much, just one song. Let's say the second and the third songs have guitar solos of 30 and 90 seconds respectively. Now the binary tree looks like this. The song with a guitar solo of more than 50 seconds is on the right, and the song with a guitar solo of less than 50 seconds is on the left. Now watch what happens when we add more songs. The tree starts to grow. How does this make music recommendations easier though? Let's say you want to recommend songs which have solos that are less than 50 seconds long. Well, all you have to do is recommend all the songs on the left of the song that has a solo of 50 seconds. Why is this fast? It's due to the same reason our search algorithm was fast. The process of splitting our data into half using some order makes finding that data easier. And on average, it will take the natural logarithm of n comparisons for you to search for music in this binary tree. Congratulations! You now know how a binary tree works. I want to end this video with a quote by Edsger Dijkstra. Recursion is a beautiful, yet subtle and delicate concept, which requires careful handling. In a world where the latest buzzwords start with A and end with I, we seem to forget about the deceptively simple concepts that made all of this innovation possible.